Beneath our feet, massive tectonic plates are constantly pushing against each other. When that friction finally overcomes the rock's strength, the plates slip, releasing violent, unstoppable waves of kinetic energy. On June 24, 2026, that energy tore through the dense metropolitan areas of Caracas and La Guaira in Venezuela in the form of a magnitude 7.2 and 7.5 doublet earthquake. The human and structural cost was devastating. Over 920 people died, and more than 250 rigid residential buildings completely collapsed into rubble. But within that exact same 36-hour window, two other major fault lines ruptured. A magnitude 7.2 earthquake struck off the northeastern coast of Japan, and a 5.6 hit Northern California. This split-screen chart compares the outcomes of these concurrent events. Notice how the magnitude, fatalities, and collapsed buildings stack up. While Venezuela suffered catastrophic losses, Japan and California recorded 0 deaths and 0 structural collapses. These outcomes reflect decades of financial and engineering decisions embedded in each city's built environment. Cities face a brutal calculation. They can absorb massive upfront capital costs to adapt infrastructure today, or pay the catastrophic price of structural failure later. To evaluate how we protect our urban centers, we need to look at the specific, modern engineering strategies that actually prevent total structural collapse. And more importantly, we have to weigh the real-world economic and logistical trade-offs of implementing them. To understand how to save a city, we have to compare the traditional methodology of building for sheer rigidity against the modern standard of controlled flexibility and digital awareness. For decades, the structural engineering industry tried to out-muscle earthquakes by making buildings unbendingly rigid. Today, that approach has been replaced by designing structures that deliberately deform in controlled ways. This cross-section diagram details the 3 approaches to seismic engineering. In Japan, standard practice has moved entirely to the 2 systems on the right, vibration control and base isolation. Look at the diagram on the far left. Traditional rigid construction forces the building to absorb the full, violent lateral force of the seismic waves, risking a fatal column failure. Now look at the base isolation design on the right. By installing rubber bearings and shock absorbers, engineers physically separate the building from the ground, absorbing kinetic energy before it travels upward. To understand how the ground moved, seismologists rely on finite fault models mapped by agencies like the USGS and Italy's National Institute of Geophysics and Volcanology. These models extract the physical mechanics of the rupture, the depth of the tear in the crust, the angle of the slip, and the exact velocity at which the energy traveled. Shallow, right lateral strike-slip earthquakes move the ground sideways. On the exact same day, an earthquake releasing a mathematically similar amount of energy struck Japan. Their urban infrastructure absorbed the blow and remained standing. This map illustrates the macro-tectonic boundary between the Caribbean plate and the South American plate. Along the northern coast of Venezuela, this boundary concentrates into a specific active structure, the San Sebastian Fault segment. This is a transpressional boundary. The plates grind past each other in a right lateral strike-slip motion, accommodating about 10 millimeters of slip every year. Over centuries, this sideways friction stores immense horizontal shear stress. The plates are locked, but the directional momentum continues to build entirely along a horizontal plane. On June 24th, that stress exceeded the friction holding the rock together, triggering an initial rupture in the Yumare-Moran area. Because of the right lateral geometry, the kinetic energy delivered to the surface is overwhelmingly horizontal. Looking deep into the lithosphere, the INGV finite fault model plots the San Sebastian fault plane dipping 75 degrees to the south. The sequence begins near Moran, initiating at a depth of 20 kilometers. Over the next 20 seconds, the rock violently shears, creating up to 2.5 meters of lateral slip. Then the ground temporarily stabilizes. There is a precise 39-second gap. That initial 7.2 magnitude rupture actively rearranged the stress field. The 2.5 meters of movement effectively removed the friction holding back the adjacent eastern segment of the fault, Those 39 seconds acted as a compounding loading phase, leading to a second, more violent rupture. Directly east of the foreshock, the fault tears again, initiating the magnitude 7.5 main shock. This second event occurs much closer to the surface, at a depth of only 11.1 kilometers offshore of Katia Lamar, and displaces the rock by a massive 3.6 meters. The raw displacement size dictates the volume of energy, but the rupture propagation velocity determines how that energy is delivered. The INGV calculates that this rupture tore through the crust toward Caracas at a blistering 3 to 3.5 kilometers per second.